This is an automotive shock. Its purpose is to absorb mechanical vibrations caused by bumps in the road. In motorsports, the characteristics of a shock are carefully picked to control how a car behaves in the middle of a corner. In essence, the shock controls how fast the wheel moves up and down during its travel. As you can see, it's actually really easy to compress. That's because the faster you compress it, the more force it applies. Shock absorbers transfer kinetic energy into thermal energy by pushing viscous fluid through holes in a piston. Unfortunately for racing teams, it's difficult to measure this rate of energy transfer if they use spares or need to confirm characteristics from a manufacturer. Right now, if any of these teams wanted to test these characteristics like the damping ratio, they would have to push on one of the corners of their car or rate how it feels while driving, which are both inaccurate. The market price for solving the problem with a shock dynamometer is $10,000, which prices most teams out, but leaves an opportunity for us. To accomplish our mission, we plan on creating a shock absorber testing device priced at $1,000, 1/10 of the market price. We're excited to share this with you at the Georgia Tech Capstone Expo.
So here we have the prototype for the shock dynamometer. The frame is solely made out of 80/20 aluminum extrusions. These were chosen because they were very structurally sound, and also there are various connection points that are easily adjustable throughout the whole frame. So here we have an adjustable rail where the shock attaches to, provided support by a mounting block right here and a force transducer right there. At the bottom we have extra support here, an aluminum rail, and then all the way in the back here we have a whole structural frame that allows the shock to not move, deform, or bow in any way, since we are outputting about 250 pounds of force onto the shock and onto the system.
Yeah, so for the linkage system, it connects to the linear bearings that help it slide up and down and translates the motion up and down. And attached to the linear rails is a linear position sensor that reads the change in position with regards to the linear magnetic tape on the other side. Also, we have this force transducer attached next to the shock and attached to the frame. This applies a voltage based on the amount of force that is applied right over here.
So here we have a AC induction motor given to us by our incredible professor. It is capable of outputting up to, I think it's like 400 inch-pounds of torque in this configuration, and that's due to the planetary gearbox that we got, which is a 5-to-1 gear reduction. So the motor will be outputting at a maximum speed of about 1,000 RPM, which is about 200 RPM at the output. So that goes directly into the shock, and based on the amplitude we're using, translates to about 10 inches per second of linear speed at the shock. All right, so for the electronics on the machine, we are using an Arduino Mega to control the unit. The nice thing about this motor is that it actually has onboard controls, so all we need to do is supply a PWM signal and on-off signals to turn it on and off and control the speed. And then we have 5-volt and ground buses for all of the sensors to make sure everything is safe and getting steady voltage so that we have accurate readings on all of our sensors.
So here, once we have our reading, we can have a test from 2 to 10 seconds. We get the force, and with the position from the linear position sensor, we convert that into a velocity, and that gives us our force versus velocity graph. Here we can see if there's hysteresis in the shock itself, and then also we can figure out the damping coefficient of the shock at low and high speeds, and then for bump and rebound. And we also have a force versus displacement graph over here to diagnose the shock if there's any problems.